I've started the class on iClicker, so if you all join, we'll start with our vote. Oh, oh. All right, let's get started. Same announcements as Monday, same announcements as Tuesday. The next Achieve is posted and due next Wednesday. I'm sure we're all so happy. I know I am about having Monday and Tuesday off, so no class on Monday for fall break. And then we're going to do this vote for the exam change. So let me push this poll to your devices on iClicker. The option is A, if you want to have the exam stay as the same dates, and then B, if you want to move them to the Fridays. So I'll give you all 30 seconds to a minute to vote. And then I have another section, so I'll compile all of the votes, and then I'll post an announcement today about the exam dates. Let's get our votes in.
Not letting me do anything else.
Oh, it says answer received, so I think that's fine.
Oh, and I just stay on the screen?
I think so.
Okay.
It's set up differently this time because I didn't set it up as a quiz ahead of time.
Oh, okay.
I just did a poll now, so I think it just stays
like
it does
that.
this turn. Yeah, okay. Yeah. All right, I'm giving you 10 more seconds. All right. If you're just getting here, don't worry. This is not for credit. That was just for the exam schedule. Okay, so we are moving on. Wednesday, we talked about these solubility guidelines. Everybody, please quiet down. We're starting the class now. All right. Okay, we talked about these solubility guidelines. So most ionic salts, or most ionic compounds, dissolve into ions into solution. We can use these guidelines to determine when we do a displacement reaction if the new ionic compounds, or if any combination of ions in solution, will form a solid. So one of the questions that we didn't get to was this learning check here. And we're looking to find all of these soluble salts. So let's go through these. We have silver nitrate first. And if we go back to our solubility guidelines, nitrate is under guideline 1, and there are no exceptions to guideline 1. So this is a soluble compound, or soluble ion. So if silver nitrate is in solution, it will remain as ions. The next one, barium hydroxide, this is one of our strong bases. We can look to the solubility guidelines, and it follows solubility guidelines that this is a soluble salt. But we also know that it's a strong base, and strong bases dissolve fully into their ions. Next we have NaCH3, CO2. CH3CO2 is under guideline 1, and sodium is a group 1 metal cation that's also under guideline 1. So both cation and anion are present under guideline 1. Both are soluble in solution. So this one is soluble. And last we have lead 2 sulfate. So if we go back again to the solubility rules, sulfate is under guideline 2, but there is an exception to guideline 2, and that's if you have any of these atoms with sulfate or any of these metals with halogens. In this case, we have lead sulfate, so that's an insoluble exception to guideline 2, so that compound is not soluble. This would stay as a solid in solution. Okay, that was really quick, but just a reminder that those are our solubility guidelines. There are a lot of practice questions on Achieve about looking through these guidelines. Another thing we did at the end of class was write out this ionic equation. So we earlier in the class did a double displacement reaction with those two starting material ionic compounds, aqueous and solution. We determined that a new combination of a cation and anion does form a solid, calcium sulfate, and then the other remains aqueous. That on top, that's the total ionic equation. Just the ionic equation, we separate everything into its ions if it is an aqueous compound. So calcium chloride, we separate into the calcium cation, chloride anion. That's because if you add calcium chloride into a beaker of water, it will separate into those ions. You will have calcium 2 plus and chloride 2 minus. Same with potassium sulfate. So those separate into their ions. We know that because in the original equation, it has aqueous next to it. So it tells you in solution, it stays as ions. The calcium sulfate, this is a solid. So this remains as a solid. It doesn't get dissolved into water. So we keep it as a solid. And then potassium is aqueous and chloride is aqueous as well. Then the net ionic equation, we cancel out any spectator ions. These spectator ions are the ions that are present on the product side and the reactant side. So we can cancel out anything that's present on both sides, and we get the net ionic equation, which shows really the formation of that solid. Okay, so we did that quickly at the end of class. Let's do another one. I'll have you all work on it for a couple of minutes and then we'll go through it together. So we have the total reaction equation that's already given to us. You see we have two aqueous starting materials or reagents and then a solid and an aqueous product. So start with writing the ionic equation, so showing all of the ions, and then the net ionic equation, canceling out anything that's on both sides of that reaction arrow. All right, let's go over this together. I'm hearing some good conversations as you're working on this. So our first task is to separate anything that is aqueous into its individual ions. For silver nitrate, nitrate is the polyatomic ion with a -1 charge. So they're in a 1-to-1 ratio, silver and nitrate. So silver must have a +1 charge, and that is aqueous. So it's the ion dissolved in solution. You can write the charge as +1 or 1+. I'm sure you'll see both versions. Either one is fine with me. So we have silver +1, nitrate, NO3-. And then we have sodium chloride. Sodium, first column of the periodic table, +1 charge. And chloride, -1. And remember, we always keep polyatomic ions together, so that's why we have NO3- as its own ion. So these are all of the reagents. And then going to the products, silver chloride is a solid product, so that stays as a solid. If you were to look at the solubility rules, you'll find that silver chloride is not soluble in water, so it remains a solid. If you had a beaker of water and a sample of sodium or of silver chloride and put it into that beaker of water, it would not dissolve into its ions. It would stay as a solid. So we have silver chloride, a solid, and then sodium +1 charge, and nitrate, NO3-. And that's our that's our ionic equation. So every ion is represented. When we draw out the net ionic equation, we cancel out any ions that are present on both sides. For forming a solid, it's kind of helpful to start over here and see what ions are here. We have sodium and a nitrate. Otherwise, we have the solid, so nothing can cancel out for the solid. So sodium on this side is on both the reactant and the product side, so that will get canceled out, and the nitrate. So our net ionic equation is silver with the +1 charge, chloride, the -1 charge, to form silver chloride. Another note here, it's okay to just put the plus or to put the number. I don't know why I chose to do the 1 for silver and just a plus for sodium. Either way is fine. Achieve might want it a specific way though. Does anyone know if you've done it? What do they want? Just a plus or a minus? Okay. I'll just take out the 1 then. It means the same thing, but if Achieve wants the plus or the minus, keep that in mind. And it wants a number first? That worked for you? Okay. Good to know. Okay, questions on this process, writing ionic equation and the net ionic equation? Yes. The 2 ions that are present in the solid are on the left side and on the solid on the right side. All right, we are moving to section 4.5, acid-base reactions. So we'll predict the products of acid-base reactions and then write and interpret the ionic and net ionic equations for these reactions. So we're talking specifically about the Bronsted-Lowry definition of acids and bases and acid-base reactions. There are other categories of acids you'll learn about in the future, you may have learned about in the past, like a Lewis acid. For this chapter, we're focusing on Bronsted-Lowry acids, Bronsted-Lowry bases, and Bronsted-Lowry acid-base reactions. Bronsted-Lowry acid-base reactions are defined by having a transfer of a hydrogen cation or H+. H+ is also called a proton. It's very, very common to refer to the H+, the hydrogen cation, as a proton. We call these reactions also proton transfer reactions. The reason we call this a proton, H+, is because if you look at the periodic table, hydrogen is our first element. Its atomic mass is 1. So neutral hydrogen atom has 1 proton, no neutron, 1 proton, and 1 electron. That's a neutral hydrogen atom. If we have a hydrogen cation where we've removed an electron and now it's positively charged, all that's there is a proton. So that's why we call H+ a proton. And in a Bronsted-Lowry acid-base reaction, the acid donates the proton. So in the reaction, the acid starts with the hydrogen cation and then gives it away to the base. And so the base accepts that proton. So here we have, the next slide is an example of an acid-base reaction. We're starting with OH minus. Right now we don't have any counter ions, so there's no cation with the OH minus or anion with the H3O plus. That's okay, we're just focusing on the hydrogen transfer that happens between these 2 atoms. But if you look here, we have OH minus and H3O plus. In the products, we have H2O and H2O. So that means that an OH minus anion gained a hydrogen, and we got H2O. And the H3O plus cation gave away a hydrogen, and we got H2O as the other product. So that makes H3O plus the acid. This donated the proton, a hydrogen ion donor. OH minus is the base, it accepted the proton, so hydrogen ion acceptor. And you'll see we start with 2 charged molecules, 2 ions, and we have 2 neutral molecules as a product. So this reaction is also called a neutralization reaction. because the acid and the base are neutralized in charge. And this is the driving force for acid-base reactions. In this particle picture, you'll also see that for this reaction to occur, the acid, which has the proton that's going to get donated, collides with the base that's going to accept the proton, and that's what they're showing right here. So hydrogen from the acid, during the collision, is transferred to the hydrogen, or transferred to the base. And that's how we get the two H2O molecules. Here's another example of a proton transfer between now HCl and H2O. So hydrogen chloride, that is a molecule that's on our list of strong acids. So it's going to donate a proton to H2O. So this is the strong acid, then in this case water is going to be the base. It's going to accept the proton. So H2O acts as the base. We show the collision here where the hydrogen, smaller atom than chlorine, so this is the hydrogen and HCl, collides with the oxygen and H2O. And then we get H3O plus, hydrogen donated its, or HCl donated its proton and lost it. So now we have H3O plus and Cl minus as the products. So some acid-base reactions you'll see represented ending with charges. That's okay, that still happens in acid-base reactions. Some of them are neutral, end with neutral products. When we do our ionic equations, we'll see that the products are neutral water products. Okay, so this is with a strong acid. We have a weak acid. So the difference between strong acid and weak acid, strong acids fully ionize into the H plus cation in their anion. Weak acids, when they're added to solution, so if we have like a milliliter of a weak acid added to water, some of that weak acid sample will dissociate into the H plus cation in the anion, but some of those acid molecules will still stay together as a full neutral molecule. So if you have a weak acid in solution, then it will only donate part of its ions. Some of it will stay together. But if for the hydrogens that are donated, we then would generate the anion from the acid, and then in this case H2O. Same process is happening when that reaction occurs. Hydrogen donate, or the acid donates its hydrogen, loses its hydrogen to the base. I think that's all I want to say on that slide. Similarly, if we have weak bases, these do not readily accept protons. Some of the weak base molecules will accept a proton, some of them won't in solution. So they remain primarily in their unprotonated form, meaning they haven't gained a proton yet. They're weak electrolytes. And then this base that's shown here, NH3, this is ammonia. That's a common weak base. That's one that you should remember as a weak base. So if you have NH3 present in solution with an acid, the NH3 will gain a proton and become NH4 plus. So it's gaining a positively charged hydrogen. So we have an extra hydrogen, NH4, and then a plus charge because it gained a cation. So we have NH4 plus. And then H3O plus was the acid. It donated a proton. We get H2O as the product. Okay, so we can write ionic equations for acid-base reactions. We'll do this one together, and then I'll have you all try the next one. So we're going to write the total reaction equation, the ionic equation, and the net ionic equation for acid-base reactions. we have a strong acid and a strong base. These are both on our list. HCl is a strong acid, KOH is a strong base. So when we do the total reaction equation, we start with our aqueous compounds. And we are essentially doing a double displacement reaction. Hydroxide from potassium hydroxide will combine with the proton from HCl, H+. Potassium from potassium hydroxide will combine with chloride, the Cl-. Now when you have OH hydroxide combining with H+, a proton, that's water. We have H2O. You can think of water as HOH, so hydrogen from HCl and the OH from potassium hydroxide. But we represent that as H2O. We're talking about these compounds being soluble in water. H2O is water itself, so it's not aqueous, it is just a liquid. And then our other product is potassium with chloride. Yes. Well, you can assume these are at room temperature. So if they're at room temperature, it's at a liquid form. So yeah, you can assume liquid, unless it specifically says it's above boiling point of water. All right, so that's our total equation. We did double displacement. We formed water, which is a liquid, and then KCl, potassium chloride, which is aqueous, dissolves in solution. The ionic equation, now we're separating everything into its ions. So we have H+ cation, Cl- anion, potassium cation, hydroxide anion. Hydroxide is a polyatomic ion, so we keep the OH together. This forms H2O as a liquid, so this is another component that we don't break into ions. We keep that molecule as H2O. Then we have potassium cation as a product and chloride anion as a product. And then we follow the same procedure to write the net ionic equation. We cancel out any ions that are present on both sides, so spectator ions. Again, we can start over here. We're going to keep H2O as a liquid. Potassium and chloride, as long as they're on the reaction side, then we'll cancel them out, and they are on the reactant side. So we can cancel out potassium and chloride. And our net ionic equation is H+ plus OH minus, forming H2O. I'll leave this up for a minute, but once you're done, go to the next slide and try writing out the total equation, ionic, and the net ionic. Okay, so so here, part of it okay, so this is, I'm assuming that would be but the barium, that's all of the metal. So this is important. And then OH minus. So barium is OH minus. So we draw the product. Yes. Yeah, so you're right, there's two. Same with substance. Like here, there's two. All right, let's start going through this next one. There's a lot of different concepts that we're pulling in, even when we're just writing that total reaction equation. So if we're starting with HCl and barium hydroxide, we're doing a double displacement reaction. So we take the cation from one and the anion from the other and pair them together. So if we do that with hydrogen, which is our cation here, and OH minus, which is the anion, then we have HOH, which is water, H2O. And then we pair the cation from the other barium and Cl minus, and we have Ba. Now, in barium chloride, barium on the periodic table is in column 2, so it has a +2 charge. Chlorine is in the 7th column, so it has a -1 charge. These are charges that you should remember. So since we have barium with a +2, we need 2 chloride ions to create a neutral molecule. So the molecule is BaCl2. And then if we look at solubility, we'll find that that's a soluble compound. So we have all of the compounds, but this equation is not balanced. We have 1 chlorine on the left, 2 chlorines on the right. We have 1 or 2 hydroxides on the left, 1 hydroxide on the right. So after writing out all of the compounds, then you need to balance the equation. We balance the chlorides. We have 2 on the right, we need 2 on the left. So you can put a coefficient of 2 in front of HCl. Balance the hydroxides. We have 2 on the left, BaOH2, and only 1 on the right in H2O. So we need a coefficient of 2 in front of H2O. And then we need to check, barium is good. We have 1 on either side. We need to check hydrogens. We have 2 hydrogens total from HCl because of that coefficient of 2. We have 2 hydrogens total from barium hydroxide with a subscript of 2, so that's 4 total. On the product side, we have 4 total hydrogens as well. So I went through that kind of fast. We talked about balancing equations Wednesday. If this is too fast, then I recommend going through and writing out every atom like we've done in the past. So HCl, we have 2 hydrogens, 2 chlorines. Barium hydroxide, we have 1 barium, 2 OH minus ions. Do that for each molecule and make sure you have the same atoms on either side. We have, yeah, go ahead.
Do we have to worry about balancing it since we're just going to separate everything out anyway?
We should balance it. Yes, we do need to balance it. Yeah. When we do the net or the ionic, I'll explain why. Okay, so we have our balanced equation. Now we need to write the ionic equation where we separate everything into their ions. Do you have a coefficient of 2 in front of HCl? That means that for this balanced equation, if we separate that into ions, we have 2 H plus ions and 2 Cl minus ions. We have 1 barium plus 2 cation and 2 hydroxide minus 1 anions because of that subscript. So we both take into account subscripts and coefficients to multiply the ions present. If you have 1 barium hydroxide mole that you add into a solution of water, for every 1 barium 2 plus ion, you have 2 OH minus anions. So we need to use that coefficient there. Then we have 2 H2O. And then barium chloride, we have 1 barium 2 plus and 2 Cl minus. So here's where if we didn't balance the equation, we wouldn't be able to write the correct net ionic equation. Because we form barium chloride, we have 2 Cl's as a product. If we didn't balance the equation and didn't have a coefficient of 2, we would only have 1 Cl over here, and then we wouldn't be able to cancel them out on either side, but they should be canceled out. All right, so that's our ionic equation. To write the net ionic equation, we cancel out spectator ions. In this case, Cl minus and Ba2 plus. And then here's our net ionic equation. But we're not quite done yet. When we write out balanced equations, we use the lowest ratio of coefficients possible. Here we have 2, 2, and 2, so we should reduce that to 1, 1, and 1. So we have H plus, OH minus, H2O. And you'll notice this is the same net ionic equation as the previous example. So whenever you have a strong acid and a strong base present in solution, you'll form H2O, and this will be your net ionic equation. Not everyone is looking like I got it. So what can I explain that will help you all feel better about this content? Okay. Yes. Yeah, so this will be the correct final net ionic equation. Anytime you balance equations, you'll check the coefficients. If you can use a lower ratio for all of the coefficients, then you should.
Okay, so like, let's say it's like somewhere 2 and somewhere 4. Would it be like 2 divided by 2?
Yes. Yes, then you'd have 1s and 2s. Yeah, if there were 2 and 4 coefficients, you'd reduce to 1 and 2. Yeah. Yes, go ahead.
So like after you balance the equation, you can kind of just go through the equation like you want to do it, except for like making those coefficients.
After you balance the equation for doing like ionic and net ionic, yeah, same process. After you balance it, same process as for ionic compounds. Yes.
So what if, for example, the H2O was a 3 and we have to divide it by 2?
We wouldn't. Yeah, so we don't use any fractions as coefficients. So for any reaction equation, you have a 2, and a 3, then that's the coefficients that you keep. If it was 2, 2, and 6, then you could reduce. So I always keep whole numbers for those.
So when you get the net, will it always cancel out, or will it
Are you referring to the ions cancel out? I suppose if both compounds are solid as products, then nothing will cancel out. Yeah, that's possible. Yeah. But if you have ions on the right, you probably have the same ions on the left, and those will cancel out. Yes.
Each thing, or could we just, that's a part
Like actually writing these
Yeah.
lines? No, I think if you have the ionic and then the net ionic, I can deduce that you canceled out whichever ones you chose, yeah. Okay, all good questions. Thank you for giving me questions. That's my favorite part. Okay, a little bit more about weak acids, and then we're moving on to a little bit more about naming. So if we have a weak acid, acetic acid, I mentioned previously, this is a weak acid. If it's present in solution, some of the molecules of acetic acid will donate a proton, act as an acid. Some will remain as the full acetic acid molecule. But if you have acetic acid in the presence of a strong base, like hydroxide, this is a strong base that's going to drive the acid-base reaction forward, and it will react until all of the hydroxide has then become H2O. So the goal or the purpose of the slide is to show that if we have to look at the strength of both the acid and the base. So you could have a strong acid and a weak base. The strong acid is going to react until it's donated all of its protons. Or you could have a weak acid and a strong base. Strong base will accept all of the protons that it can. You have a strong acid and a strong base, all of the ions form water, like the two previous examples that we did. We all paying attention? Yep. We all paying attention? Cool. Great. Let's move on to naming. So there was a slide when we did our naming unit where we said if we have molecules with hydrogen, those follow a bunch of different naming rules. So we're going to talk about some of those rules here. And this is when we have specifically acids in solution. So something like HCl, when it's a gas, we name it like an ionic compound. We have H plus and Cl minus, so hydrogen chloride. Hydrogen sulfide also, we have that as a gas. We name it like an ionic compound, H plus and S2 minus, hydrogen sulfide. But if these two are present in solution, so aqueous now, they follow different naming rules because now these are acids. They're able to donate a proton. We have gases. These gases, we don't really do acid-base reactions in gas form. We do them in aqueous form. So we use different names when these molecules are aqueous. So for binary acids, we have hydrogen and then another nonmetal. We use the naming pattern hydro first, and then a root from the other nonmetal, in this case chlor for chlorine, and then ic acid. So two atoms, hydrogen and something else, we have hydro, in this case chloric acid. For most atoms, we just use the first syllable of the element name, so chlorine, we use chlor. But for phosphorus and sulfur, we use two syllables. So here we have hydrosulfuric acid, and phosphorus, if it was H3S, would be hydrophosphoric acid. So that's for binary compounds. I think the next is let's do this clicker. And you're just selecting the compound that does not follow that naming pattern, hydro something ic acid. And we're gonna do this one kind of quickly because I want to get to 2 more slides before we're done. Yes. That's on the next one, so it is different. Oh yeah, so for this question, Okay, I'm gonna do 15 seconds. Cover the next slide. You need that information for the achieve. All right, 2 seconds. All right. For this one, it is C. We do not have a binary acid. There are 3 atoms here, so we have a different naming rule. This naming rule is on the next slide. This is when we have oxo acids. So the name that we use for the acidic version of these polyatomic ions are based on the name of the polyatomic ion. So HNO3, we have a nitrate ion with hydrogen. When the end of the polyatomic ion is 8, then we have ic as the end. So instead of nitrate with a hydrogen, that's nitric acid. And then sulfate, sulfuric acid. If we have ite for the end of the anion, polyatomic ion name, like this is chlorite, but with a hydrogen, then the acid name is chlorous acid. And this occurs when there's a hydrogen there, a hydrogen cation. And then for phosphite, we have phosphorus acid. Yeah. That's just not how chemistry has defined the names of these acids. Yeah, so writing the name nitric acid implies that we have the nitrate anion with a hydrogen inside, because the chemist said so. All right, we'll have to end there. Enjoy your fall break. I hope you get to rest. Thank you.